Fabio. I'll tell you about our work with I did with my student Granit Luzhnica about background perception of messages transmitted with a vibrotactile display. So we started this work with the question: what if we could feel messages in real time without using hearing or vision? And this is a picture of our experimental design and device. Well, you'll see it later. But this started in 2016, and so far we built a system to encode messages from the English language, where we designed the stimulation method, a method called overlap spatiotemporal stimulation, where we activate motors in sequence after a 10 millisecond gap. And this gives us good discriminability and a very fast way to encode a pattern. Then we designed also 3 wearable displays, and we designed an encoding and an optimized encoding of the English alphabet. And the optimization is a topic of a paper that we are going to be presenting at CHI, so it's not going to be here. But we also designed a training method. And back in 2016, when we started, we proved that people, after training for 5 hours with our method, after training for 3 hours with our method, they could already perceive the alphabet and decode it. And they could, after 5 hours, also receive letters and words and short messages with 95% accuracy. So this is how it looks. So the user in the right hand is wearing a glove, and there are 6 vibromotors in the glove. And you can see he receives the stimulation, and in this case he has to answer what word was stimulated after training for 5 hours. So it's just a video of how it works. But the question that brought us to this paper that I'm presenting now is, okay, can people perceive and decode these tactile messages while performing another task? So right now, until here, all our studies had been on actively training and focusing on decoding the tactile messages. And what we wanted to figure out is, can people do it when they're doing something else and focusing on something else? So this is the topic of this paper. This is a bit of related work of several approaches that have been in research in the past, and the oldest one is from 57 from Gildart, and several years passed with no further research. Back now, since 2016 or 2013, there have been several different approaches. We're still going to rely on ours because basically it's the one we have, but also because it's the fastest one and the most accurate one documented, okay? So where people are more accurate in receiving words and letters and words. So LA there is letter accuracy, and it's 97%. Word accuracy is 90% after training for 5 hours. Okay, so, but what about background perception? So the context or related work or context in this case is that while multitasking, people prioritize or ignore certain stimuli when they have their attention resources are overtaxed. And there are 2 types of processes. Some processes are automatic. That means once we learn how this works, we don't require much effort from our brain to do that. For example, driving is partially automatic. So our muscles are trained already on what we have to do, and basically we just do it automatically, same as riding a bicycle. We always never forget how it works. But then some things are controlled, and when you have to control the process, then you have to think about it. And this then competes with your working memory. So basically, in previous work, Lee and Starner evaluated the perception of 3 vibration patterns using a visual search task with 3 difficulties. And I'm mentioning this because we're going to use the same task to evaluate our vibrotactile display. In this case, our hardware is like this. We have an Arduino Duo board. We're using 3.4 millimeter vibromotors located in 7 spots as shown in that glove, in our 7-channel glove display. And we're using something we call overlapping spatiotemporal stimulation, which creates patterns like this one here, where instead of stimulating a pattern where 2 motors have to be stimulated, instead of onsetting the 2 motors at the same time, which would be spatial stimulation, or onsetting one after the other, which would be spatiotemporal, we do a small shift. We take most of the activation time, which is 100 milliseconds for both motors, and we activate the second motor only 10 millisecond gap after. In some of our studies, we proved that this gives you a good discrimination, so people know that there are 2 motors active and don't confuse them. And at the same time, it's a very fast pattern. So it's almost as fast as doing the spatial stimulation, which is far less accurate. So these are the methods that we're using. And now, well, to our user study, the goal is to test whether participants decode haptic messages received while performing a cognitive demanding task, right? So we have a primary task, which is a visual search, and the secondary task is we will transmit some code, and they have to tell us what it is. So these are the conditions of the study. The primary task was to find a number in a number soup. The numbers are from 1 to 99, randomly assigned. And there are 3 difficulties depending on the size of the data set. So 9 numbers, 25 numbers, and 36. And this is based on the already proposed task from Lee and Starner. And this lasts for 5 milliseconds, so for 5 seconds, sorry. And the secondary task is our vibrotactile task. We chose 10 characters, not the 26 characters from the alphabet, just 10, just to keep the study to a manageable size. And we have characters in our alphabet which are encoded with 1 or 2 vibromotors, so we choose 5 and 5. Okay? And of all the search tasks that the user had to perform, in 50% of them, there was after half a second the vibrotactile task. Okay, so I'll show you how it works. This video shows you a participant performing the task. So the right hand is the device. So it's a very prototypical device, as you can see, because it lets us fit the hand of any person. So we didn't build a single glove with the motors embedded. We have a glove, different gloves for different hand sizes that we can fit the motors where we want in the right position. And this is the participant performing task in real time. Okay, I show you how the task looks like on the screen. So here, you can not see it, but the glove is vibrating while the participant has to answer the questions. So this video shows you in the screen how it looks like, and you can try to solve the visual search while the video goes on. So in some cases, so all the conditions are randomized. In some cases, the user even doesn't find the right answer, like in this case. He said the target was not present, but it was in the numbers. I can play it again later if you want to see the case. Well, I just want to tell you, okay, the study procedure was like this. We had participants training for 5 days, 1 hour a day, to learn to use the interface. And then this is not contemplated in this study. We just took the participants right after and performed the study that I just mentioned here as a follow-up. And so I will not report on the progress here. Basically, what our experiment had a first task, which was a recall task of all the 26 letters. So we tested that they could recall, that they had trained all this, and they could do it. And this we call VVO, so vibrotactile only. Then there was the dual task training, which had 2 times 2 letters and 3 times, so the 3 versions of the visual search. And then there was the real experimental dual task with for 2 letters, 3 visual search tasks, and 3 data set sizes. So to summarize some of the results, so this is the first part, is the recognition of vibrotactile stimuli. We had 7 participants, 6 male and 1 female. And we found that the accuracy is comparable. So you can see here in this graph, the search, the size of the search set is 0, indicates the vibrotactile only task, and the vibrotactile accuracy. So the accuracy in decoding that there was a message coming, one of the letters, right? And you can see, as you can see, there was no effect basically on the recognition of the vibrotactile messages from doing the search task, right? And participants could repeat the stimuli, so they could press space to get it again. And in the vibrotactile only, it happens 4% of the time, and in this case, it happens 6% of the time. So it's also not very statistically significant. It's not even an important thing. On the other hand, we want to know if the visual search task got influenced by having to decode these vibrotactile messages, right? And in this case, we also found no statistical difference. We found some curious results when the search size, when the data set size was 25 items, they had worse performance, let's say, than when it was 36 items. And when it was 9 items, it was the best case. But as none of these differences was statistically significant. So we can so these are pairwise comparisons, right? So the visual search only to each of the 3 cases when they had a stimulation at the same time. So at the end of the vibrotactile phase, and also at the end of the dual search task, we had a TLX questionnaire that they had to fill in for each of the cases: vibrotactile only, visual search only, and visual and vibrotactile. Participants basically rated that it was more cognitively demanding, so mental demand, when they had both the dual task, but the differences were also not statistically significant in this case. So basically, the conclusions of this study is that we can transmit these symbols in the background with high accuracy. So the symbols last for 100 to 110 milliseconds, and the primary task performance is unaffected. At the same time, the self-assessed workload was not significantly affected. So what we didn't evaluate is what happens if we transmit a sequence of characters to form a word. This is something that we're doing in the future. And talking about the future, I'll tell you a little bit about what we're doing now. We're planning an application. We developed an application for sensory substitution using this vibrotactile display. So the idea is, if you receive a message, you convert it to vibrotactile and you transmit it directly. Or if you use a camera to recognize a picture, you can also convert this to text and transmit it. So what we're doing is exactly this pipeline. So we have our mobile phone hanging from a necklace, and we can, using buttons of the mobile phone, set it to capture speech or to continue, so to capture once or to continuously capture. And we have some filters there, but we do speech recognition or image recognition using either the Android libraries or the Microsoft Cognitive API. For the image recognition case, we convert everything to text, and there are some filters and translation. I don't have the demo here, but trust me, it looks something like this. You receive a message, and then it's translated to, in this case, there's a picture and says, a man wearing glasses, faces, male, 36 years old. So this is what we get from the Cognitive API from Microsoft, and this is basically transmitted through the vibrotactile. So we haven't tested whether all these messages can be transmitted, how fast, how long it takes for participants to decode it. This is a work in progress. But basically, with the libraries that you have available, you can also build translation. So we're working on that part. So these are the benefits of our method. It's dynamic content, but can be presented to the user, allows a broad range of digital and ubiquitous applications, and it's very fast to learn. So we have performed 4 studies on using our method, our training method, and in every case it takes 3 hours distributed over 3 days to learn the alphabet. If you compare that with learning Braille as it's documented, it takes about 6 months to learn the alphabet for sighted people. Okay, so that's the end of my talk.
We have time for some questions.
So designing the encoding for the letters, was there a specific logic to it?
That's a good question. Thank you. Yeah. So the first thing we did in 2016 is we chose we have patterns of different number of motors. The duration is not very different. At the beginning, we had 1, 2, and 3 vibromotor patterns. So what we did first is say, we took the frequency of appearance of letters in English, so you can get this from Google, and decided to encode the letters that appear more frequently with only 1 vibromotor, because we thought, okay, these are going to be easier to detect. And then with 2 the next letters, and with 3 the most infrequent ones. We had some problems. I'm spoiling some results from the Kai talk. We had some problems, and one was that when you have two letters that share a vibromotor, then they get confused. So 2 subsequent letters that share a vibromotor. So we changed this strategy, and we use an optimization algorithm to optimize the alphabet. So there is a loss function, and then looking for bigram frequency to see that we don't have this kind of problem.
So, just a follow-up to that question. So for the experiment,
Yeah.
You used 10 letters,
Yeah.
right? And they weren't randomly selected.
Yeah.
So is it biased towards, because most of the letters are the ones which use only one of the motors for stimulation?
Well, not in reality, because we use the letters that have 1 or 2 vibromotors.
Yeah.
And we are using the second method that is optimized over the alphabet. So it's basically, we don't know if this letter is more frequent or less frequent anymore.
Okay. And just a thought, would it make sense to design encodings for commonly used words instead of
Yeah,
just
definitely.
letters, so it would be easier to transmit in like single stimulations.
Yeah, definitely. So the point is, it depends on how many
Yeah,
motors you have, how many patterns you're going to be able
yeah,
to produce. And if you put more motors, they become too close to one another, and then you cannot discriminate between one and the other because our sensitivity is very low in the tactile. So this is a trade-off, you know. The other thing you can do is with 10 symbols, instead of encoding letters, you can assign them to some meaning, like a sentence that says, I don't know, going to supermarket or
yeah.
go by the school or stuff like that, and then you just assign what symbols you want to receive, and then when you get the message while you're driving or something, then you know what it is, you know, and you only need 10 symbols then.
Thank you.
Let me say, you're saying about using sensitivity. Yeah. Yeah. So basically, we are using sensitivity for something else. So we're using sensitivity of the skin to decide how you onset the motor. So we made a study where we learned that depending on the sensitivity, if we prioritize on sensitivity, we are more accurate. So people are more accurate in decoding the message. So basically, we're using the sensitivity of the skin to do that.
Sure. One last question. Sure.
So,
Thanks.
I have like two questions.
Yeah.
So one is, did you encode force into, oh, sorry. Did you encode the force of the sensors? Like maybe the force of the sensors
No.
can represent.
So we tried.
Oh, okay.
We tried in one of the studies changing the frequency and amplitude as to encode symbols, and this was not very discriminative. So we're trying to just using the position and the activation order, you know, because this was more discriminative.
And my second quick question is, how does this compare to traditional dot text methods? Like, are there like performance increases, or there are other benefits than like the
In
dot text? Yeah, like when
like
people
Braille.
touch the text. Yeah.
Yeah. It's much faster to learn. Braille, good experienced readers can read faster than what we have experimented with. So we are basically in 100 milliseconds per symbol. So if you do the math, it will be 1 word per second or something like this, which is rather, it's slow compared to so visual, you can get about 200 words per minute. So it's still slow, you know. But we haven't experimented with shorter durations yet. And we've only trained people for 5 days, so we guess with experience this will get better, but we don't know yet.
Okay. You can